Oh, man. All right, everyone, good afternoon. Oh, 1 o'clock. Let's get going here. We have a test in 48 hours. You have a test in 48 hours. So how's that review going?
It's going okay.
It's going okay?
Yeah.
Raw derivatives. I like the way you worded that. And then I just got to do the dy over dx and then the word problems.
Yeah. Well, I'll be in my office tomorrow if you need help. And then before our test on Wednesday, or sorry, on Thursday, I'll be in my office from 10 a.m. till class starts. So if there's anything you want to run by me, you can. My intention is to not hand out the solutions to that. I think I said that last time. So, and you're also free to form your own study groups. You can get together, you know, email each other or create a Zoom call between each other if you want to go through things. All right, so last class we were talking about related rates, and all of you were really falling in love with the idea of these problems. No? Okay, well,
That's correct.
I got this sense that you were falling in love with it, but I could be wrong. So we did a problem where a plane was flying overhead, right? Remember this problem? And we were saying at a specific point in time, how fast was the distance between the plane and the radar station changing, right? We went through that whole problem. I have another problem for you, but it's going to look the same, but it's not. So let's take a look at it. We're going to work through it. It's the same plane. It's flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the angle of the tracking radar changing? So now what we want to imagine is that this radar is moving. And if you don't want to use a radar, just think of it like we were trying to shoot this plane down, and we had an anti-aircraft gun that we were trying to shoot this down. We would have to know at a certain instant how fast our gun needs to rotate at that instant in order to shoot it down. Does that make sense? So at an instant in time, instead of talking about the distance between the two things, it's more of the rate of change of the angle. So I'll show you a picture of this. So here it is. Make this bigger. So the plane is flying overhead, and what we're interested in is this change, this rate of change of this angle. And just watch the angle for a second. It's real slow here, then it's fast, and then it starts to slow down. Real slow, fast, and then slow, right? So I like to give you another analogy. If you're like standing watching a car race, I don't know, you know, cars race around or something, a track, and you're standing on the side and you're watching the car come, your head's going to be looking at the car and it's going to be slow. Your head's going to turn slowly following the car, but as the car gets right in front of you, your head's going to have to turn fast to keep up with the car. So it's like, you know, right? And in the middle there, your head is turning faster, but as it gets further away, your head doesn't have to turn as fast to keep up with the car. Hopefully that makes sense to you. The rate of change of the angle is not constant. Even though the car or the plane might be flying, car might be driving by at a constant speed, your head is not turning at a constant speed. Does that make sense? Okay, let's do it then. It's going to be the same idea that we had before. I'm going to draw a couple of pictures. Here's the radar station. It's just going to be a dot there. Here's the plane. It's going to be a dot. We know that the plane is flying overhead. We know it's 600 miles per hour. We know that the altitude is fixed at 2 miles. So we know distance from here to here is 2 miles. And this time, we're not interested in the distance from the plane to the radar station. We are interested in the angle So I'm going to draw a line connecting these two, but instead of talking about this as being like H or whatever we want it to be, we're going to be talking about this angle theta. And so as that plane goes over, this angle theta changes. Agreed? Also from last class, we talked about when we went and tried to write down, oops, I need the instant in time picture. Here, I'll make my life a little easier here. No, I'm not going to make my life easier. Oh, come on. There we go.
I'm here.
Oh, we were waiting for you. Okay, let's proceed, class. Okay, so at the instant in time, this is our general picture. This is the instant in time that we're talking about. At the instant in time, the plane needs to be 6 miles away from the radar station. So this is 6 miles. And now let's write down what we're given and what we want. Move this over a little bit here. So we're given the speed of the plane, which is 600 miles per hour. And that's a speed, so it's the derivative of something with respect to time. But I have not labeled any variable here that represents this 600. So this is where last class, what we had to do is realize that if you imagine a point here at the bottom of this triangle, that point is also moving that direction at 600 miles an hour. So I called this side of the triangle X, and we said X is shrinking here because X is getting smaller as the plane gets closer. So I changed this 600 over here to a negative 600 to represent the fact that it's getting smaller. And now I can call this dx dt. We want, what do we want?
Theta at 6 miles.
We want to know how fast theta is changing, right? So we want d theta dt. And we want that when? At the moment that the plane is 6 miles from the radar station, right? Okay, crap. I'm going to have to label this then. Let's go ahead and call the hypotenuse h of this triangle. And that way, when I come over here, I can say at h equals 6 miles. Any questions?
No.
What am I looking for now?
Equation.
Equation that relates what?
How fast the angle of the tracking radar is changing?
What two variables do I need to connect together?
X and theta.
X and theta. It's always going to be that and that. Any equation you can think of, looking at your general picture, any equation you can think of that would relate this X and this theta together.
Law of sines.
Law of sines. We might be able to use law of sines. I think that
You could
might
use
be.
Pythagoras.
Maybe cosine?
Okay, sorry. I heard someone say cosine. That's all I heard.
Yes, me.
Okay,
Since it's
so
adjacent over hypotenuse.
yeah, so let's write this down. Okay, let's write this down. Does everyone agree that we know from pre-cal that cosine of theta is your adjacent side over your hypotenuse?
Yes.
Yes. Okay. Now the question is, do we proceed with this or not? Think about this. When we differentiate with respect to time, and this is a critical point or a critical idea. When you differentiate with respect to time, nothing is going to turn into 1, right? Like the derivative of x with respect to x is 1, right? The derivative of t with respect to t would be 1, but anything other than t, the derivative would not be 1, right? So if we have 3 variables in the problem, theta, x, and h, when we differentiate with respect to time, we will get a d theta dt to come out. Do y'all agree? A d theta dt should come out.
Yes.
somewhere in our derivative. A dx dt is going to come out, right? And a dh dt. We should expect to see all three of those. Do you all agree? Understand what I'm saying?
Yes. Is this similar to like when it comes to the problem before with the guy in the street light where we actually didn't even need the information, like that the length was 12 feet high and we didn't need that? But
Kind of. It's actually almost the opposite of that. If we use this equation, we will have d theta dt, dx dt, and dh dt, right? Three things will appear in our equation. And look at what we're given, dx dt, right? So we're happy about that. D theta dt, we're looking for it, right? But there's also going to be a dh dt. And I know nothing about dh dt. Do y'all see that? I have no idea what dh dt would be, right? So although this equation is correct, cosine of theta is x over h, I agree with that. It introduced a variable that we don't have any knowledge of. We don't know how fast h is changing with respect to time. So I would prefer to have an equation that just has theta and x and not the h. So Carla, can you think of a different equation that would give you theta and x connected, but not h? I'm asking.
I guess we can put h in terms of x using the Pythagorean theorem since we have the 2 miles.
Oh yeah, you could do that. You could solve h in terms of x, but that's even too much work. Carla, you used cosine as adjacent over hypotenuse, right?
Yes.
Okay. Stay away from the hypotenuse. Give me another trig function.
Tangent, opposite, or adjacent.
There you go. So what if we change this? What if we say tangent theta is opposite, which is 2. Isn't that fixed? It's always 2. 2 over x. Right? That equation is valid off that right triangle. And look, it doesn't have h in it. It has x and theta, so I should expect to see dx dt and d theta dt, and that I'm going to be okay with. Understand?
Yes.
Okay, so this is what I'm going to use. I'm going to differentiate both sides of the equation. So let's go ahead and differentiate with respect to t on the left side. And then on the right side, I'm going to differentiate with respect to t. But because I'm about to differentiate, I want to remind you of what the right side really is. 2 over x is the same as 2 times x to the negative 1. And I'm doing that because I want to be able to use the power rule when I take derivative of x, right? The negative 1 will come out and all that stuff. You could do quotient rule, but this is faster. Okay, this is much quicker to do. All right, who wants to give me the derivative of the left side with respect to t? Okay,
You said who wants to? I'm sorry.
did I misspeak?
It's negative secant squared theta.
Where are you getting negative secant squared from? You're the second student who's said that. Is it written around wrong on the formula sheet or something?
It's on the trigonometry. It's on the reference page.
Yeah, that's what it says.
Does it say negative?
It says it's equal, tan is equal to secant squared.
Secant squared, not negative though, right?
No.
No, not negative.
Okay, I just want to make sure. So Cody, it's just secant squared, yes?
Yes.
Okay, all right. I just want to make sure it wasn't like a typo or something on a formula sheet because you weren't the first one to say that to me. Okay, so you said the derivative of the left side will be secant squared of theta. Okay, Cody, that takes care of the tangent. What do you still need next to that?
The derivative theta over derivative of time.
Yep, d theta dt. Very critical point right there, everyone. You're doing derivative of tangent of something is secant squared of it. Then the derivative of the theta itself is not 1, it's d theta dt. Good. Now, the right side. Who wants to give me the right side derivative?
Negative 2x.
Negative 2. So you got the negative from pulling the negative 1 out, right? Negative 2x to what power?
Negative 2.
Subtract 1 from the power, so negative 2. Okay, good. Are you done?
No.
No.
No. You still have?
Dx
D
over
over
dt.
Dx dt. So you did the power rule, negative 1 came down. You rewrote x to the negative 2. Now you take the derivative of x with respect to time, which is dx dt. And there you go. So let me just clean this up a little bit. This is secant squared theta times d theta dt equals negative 2 over x squared. I went ahead and just dropped this back down and then times dx dt. All right, good news. What we're trying to solve for is here, right? D theta dt appears here. But in order for me to know what d theta dt is, I have to be able to fill in all this other stuff. Do we know what dx dt is?
Yes, it's the given.
Yeah, that's given, right? Oh, okay, but now we have a problem. Do we know what x is?
No.
No, not like explicitly. We never wrote down what x was. Could we get x though?
Yes.
And now we can go to the instant in time. That's x, right? We can go to this instant in time and we can figure out what x is because we have two sides of a right triangle. Let's go ahead and do that real quick. Go ahead. I'm sorry.
Square root of 32.
Yeah, let me do it. Let me write it out first. So this is x squared plus 4 equals 36. And then x squared equals 32. So x is the square root of 32. So now we know what x is at that specific moment, right? So I'll be able to fill that in. Is there anything else we need? I have x, I have dx dt. This is what I'm solving for. Whoa, wait, what about this? Uh-oh. Don't I need to know what secant squared theta is? Don't I?
Another side.
Let's take a derivative of this.
No, no derivative. We're done with derivatives. Once we did this step, we're done. We need to know what secant, look, we needed to know what x was, right? And so we used the triangle to get x. If we need to know what secant theta is, let's just use the triangle again. Look, let me draw that triangle again for you down here. This is theta. This is root 32. We just found that out. This is 6 and this is 2. What is secant of theta by definition? Well, let me ask you this. Carla told us that cosine of theta was adjacent over hypotenuse, right? Cosine of theta is adjacent over hypotenuse. Secant of theta is the reciprocal of cosine, isn't it? So secant should be hypotenuse over adjacent.
So h over x.
So h over x, but we can look at this triangle now, right?
So 6 over root 32.
So based on this triangle, secant of theta should be 6 over root 32. Now I'll just state on the side, that's because cosine of theta was root 32 over 6 adjacent over hypotenuse. Secant's the reciprocal of cosine, so it's just that's flipped over. And then we're supposed to square it, right? Square it. Okay, so let's put this all together now. This becomes 6 over root 32, but we have to square it.
I have a question real quick.
Yep, keep going. Or go. Braxton, go ahead.
Do you want us in I think it was pre-cal? I think that when you call it, you would we had to rationalize it, where you'd have to multiply 6 rad 32 times rad 32 over 32, and you would get 6 rad 32 over 32. Do you need us to do that, or is that just a pre-cal thing?
We haven't had that conversation. Let's have that
We
conversation.
may have at the beginning of the course.
Did I talk to you
I
all
just
about?
couldn't remember what you said.
Do y'all remember anyone else? Did I have that conversation with you in this class about whether or not you can leave a square root in the denominator?
Oh, yeah, didn't you say that it's okay for, no, wait, was that something else? You said that it was okay, but most people, they ask for that, but it's fine. You said mathematically it's fine, right?
Well, that is true. Yes, it's fine, but I didn't know if I told you like why it is that it's okay and why people are taught that it's not okay and that, no?
Yes, we did have that conversation a while back. I remember that, but exactly what you said, I don't know, but I remember that.
No, you have to, I talk about calculators and things like that, history of.
Yes, yes, you did.
But you, Danielle, you might be remembering something from not this class.
No, I remember, like you were saying,
Y'all
like,
remember
oh,
me
it's
saying that
okay.
or
It
no?
was like at the
No.
beginning. Am I crazy? Was I here in spirit? I don't know.
Feel like you said something similar to that, but it
Okay,
doesn't-
well, look, let's finish the problem, then I'll address the question. I'll address it quickly. Okay, I don't want to take too much time on it, but it's something I do like to talk about. Okay, so Braxton, stand by for an answer to your question. For now, we're just gonna leave it alone. So we're gonna take 6 over root 32. I've got to square it, right? That's what this means. D theta dt. I'm gonna go find that. And then I have -2 over x. X was root 32, but we still have to square it. And then dx dt was -600. Okay, let's square things. 36 over 32.
Can this root go away with the square?
What?
Can this root go away with
Oh,
the
yeah, that's what I did there. Right, I got rid of I squared the top and bottom. And then here I didn't square the top because it doesn't have a square on it. This one I squared the bottom, just became just 32. And then what I'm gonna do to get d theta dt by itself is I'm gonna multiply both sides by the reciprocal, 32 over 36. And it will go away over here. That'll leave me d theta dt equals, okay, I've got 2 negatives, so I know I'm gonna have a positive answer. These 32s cancel. 2 goes in 2 once, 2 goes in there 18 times. So I'm getting like 600 over 18, which I'm sure as a decimal, let's see. I'm getting approximately 33.33 repeated. All right, let's get the units. Let's start with the easy part, the time. How is time measured in this problem?
Hour,
Was it hours?
miles per hour, right?
Miles per hour, yeah, so this is going to be hours. And then this is the part that's a little tricky, theta. Theta is an angle.
Radian, you can convert it to radians.
It'll always, your answers will always be in radians. You could convert it to degrees if need be, but this is going to be radians. So I'll just put rad for radians with the dot, radians, rad per hour. So if a plane was flying 600 miles per hour over a radar station and it was flying 2 miles high, then at the exact moment that the plane is 6 miles from the radar station, the angle would be changing at 33.33 radians an hour. That would be the instantaneous rate of change of the angle. And believe it or not, this is what we use to shoot down planes and do things like that. We have a computer that's constantly calculating these things, right? I mean, have you seen like those guns that they put on like ships to shoot down planes? And they just like track the plane. They can shoot down missiles too. I mean, the computations that are happening in there are all trying to figure out instantaneous rates of change of things. I've always said that as human beings, our desire and our need to kill one another has pushed technology and mathematics to where it is, right? Like, it's just like, yes, we need a machine that can track a missile so we can shoot it down. And, you know, it's like, it's always been that way. Nuclear weapons, right? Same thing. Okay, let's get to Braxton's question. And I'm not gonna take too much time on this. when you were in a different class, you may have been told, hey, look, if you get an answer like 1 over the square root of 2, that you're not allowed to leave it that way. You were told that you're supposed to take it and do this thing called rationalizing the denominator, which means you multiply the top and bottom by the square root of 2 over 2, top and bottom. Sorry, square root of 2 over square root of 2, which is really a 1, right? That's really a 1. So you're not really changing the answer. You're just making it look different. And what you get when you multiply across is root 2. And on the bottom, you get root 2 times root 2, which is just 2. And you're told that's the way your answer has to be written. Right, Braxton? That's what they told you? No.
Pretty much.
Pretty much. Okay. So I'm here to tell you that that is incorrect. Okay. So if somebody told you you can never leave your answer like that, that's because they were told that by somebody and they're the same answers. So if you get on your calculator right now and you do this answer on your calculator, you'll get 0.707. Okay. If you do this on your calculator, you'll get 0.707. I'm rounding. Okay. So you get the same exact answer, right? So why is it that you were told you had to do that? Like I just said, it's because whoever told you that was told by somebody else that you always have to do it. And most of the time it's not really thought through. Like what's the reasoning for it? So here's the reason why people actually needed to do this. At some point in history, we needed to do it. And it was before calculators. So before calculators, if you had to do this by hand, you would be trying to do 1 in a division box and the square root of 2 on the outside and trying to do that division. So the only way to do that without a calculator is for you to already know what the square root of 2 is. And there were certain numbers that people had to memorize, like pi. You try and memorize it as many digits as you could, and other important numbers in math. Square root of 2 is an important number. So most people back before calculators knew that that was about 1.414. And now you're doing this division. 1 divided by 1.414. This is not easy to do. Because think about the way division works, right? If I have 12 out here and 5, I say, how many times does 5 go into 12? Well, that goes in twice. Then you have 10, then you subtract, you get 2. And remember, like old school division, you're trying to figure out how many times does 5 go into 12? That's where that number comes from. Well, how many times does 1.414 go into 1? I have no idea, right? I have no idea. So what we do is we put a decimal here, we put a 0, bring our decimal up. Now we say, how many times does 1.414 go into 10? I don't know. It's not obvious. Okay, so look, what if you, instead of doing this problem, you did this thing first, okay? So what would happen if we do this? Well, now here's our new problem, right? And let's do this using old school division. The root 2 goes inside and the 2 goes on the outside. And now that's 2 going into the square root of 2, you have memorized 1.414. And now you look at playing this game is easier because 2 doesn't go into 1, right? So you bring your decimal point up and now you say 2 goes into 14. How many times? 7, right? And then you can bring your 14 down, do all your math, you'll get 0, 7. So it's much easier, end of story. It's much easier to do square root of 2 divided by 2 by hand than it is to do 1 over the square root of 2. So historically, people were told, always rationalize your denominators because there was always the expectation that later you might have to do this division by hand. But that's kind of outdated now. You understand? Like we don't need that because we have a calculator. It's going to give us the same answer either way. All right, Braxton, I hope that answers your question.
Yeah, that's pretty much answers it.
Okay.
I think I remember you talking about it at the beginning of the course. I just couldn't remember what you said, so I just wanted you
probably
to
did.
clarify.
Yeah, I probably did. You don't have to leave it. I mean, you don't have to switch it. Just leave it like this. It's fine.
I'm not crazy.
No.
I'm not crazy. You were there.
Danielle, that's still an open question. We're not going to answer that yet. I'm kidding with you. I hope that you understand I'm kidding.
No,
I feel
no,
like
it
I
looks
feel like I
sarcasm.
can kid around with you. Nowadays, you can't
Yeah.
kid around with anybody, right?
Yeah,
Get in
no,
trouble.
I get that. But yeah, no, I understand your sarcasm. I welcome it. It's hilarious. Fantastic.
Okay. Street light. Okay, we did that problem, right? We did that problem, that street light problem.
Yes, we did.
Okay. Here's a good one. A conical cup, that's a cup shaped like a cone, is 4 inches tall and 6 inches wide. Water is being poured into the cup at a constant rate of 2 pi cubic inches a second. How fast is the water level rising when the water is 1 inch from the top of the cup? Okay. We have a conical cup. So, I don't know. I hope that you've seen a conical cup before. This is like a conical cup. I remember as a kid playing sports, and we always had this big orange thing.
Oh, field
filled with
day.
ice water, and it had a little holder with these little paper cone cups next to it. And we'd pull one off and drink it. Yeah, no, they still have those.
Well, when I was smaller, yeah, they had them for field day.
Yeah, field day. Yeah, that was
Yeah,
fun.
field day.
Field day. All right, so here we go. We got a conical cup, right? And we are filling it with water at a constant rate. So we're going to start pouring water into this. And what we're interested in is how fast the water level is rising at exactly the moment that it's 1 inch from the top of the cup. So let's just see it first. I want us to just imagine we're going to start pouring liquid into this, and I want you to watch the water level rise and notice how fast it's moving up. It's pretty slow, isn't it, right now? Pretty slow. So imagine I'm pouring it. It's going to start over here in a second. I want you to notice that in the very beginning, watch how fast the water level comes up. Okay, it came up really fast in the beginning because at the bottom of the cone, it's very small volume. And if I'm pouring it at a constant rate, then initially it's going to come up fast. But as the cone starts to spread out, right, it's going to start coming up slower and slower and slower, right? So we want to know at a specific instant in time, and the instant that they're talking about is when it's 1 inch from the top, which is right there, okay? When we're 1 inch from the top, at that instant, how fast was the water coming up at that instant? Understand the question?
Yeah.
Okay. Let's go do it. Okay. Picture time. I'm going to draw a cone. Now, what I do know about this cone is that its dimensions are not changing, right? The cone is 4 inches tall and it's 6 inches wide. That never changes, right? The cone is the cone. The cup is the cup, right? But inside the cup is the water. And the water level is somewhere around here, right? Somewhere, right? And that thing is moving, right? It's going up. The water level is moving up. So I should probably put a variable to represent that level, and I'm going to call it H for the height, right? The height of the water level. Makes sense? This is my general picture. So the reason I labeled it H is because it's changing. All right, I think that that's sufficient for now. Let me see what else. Now let's try the instant in time. At the instant in time, This is still 4. This is still 6. But where's my water level?
1 inch from the top.
1 inch from the top, right? So 1 inch from the top would be
3
here.
inches.
Which what?
It would be 3 inches.
Then this H would be 3. Good. Everyone understand that? It's 1 inch from the top, which means that if it's 4 inches tall, then it's risen by 3 inches.
Do we also need a variable for the horizontal or the radius of the cone?
We might. It depends on where this leads us. Right now, I'm just trying to draw a picture of the scenario and the things I'm interested in, the things I know something about. We might need the radius, maybe. We'll see. Maybe what will motivate that is figuring out what we're given and what we want, right? So we're given something, right? The conical cups, 4 inches tall, 6 inches wide. We've got that. Which out of all of this, what is a derivative? What is a rate, a speed that we're given?
The 2 pi cubic inches per second thingy. Did I
2
get it
pi
right?
cubic inches per second is given. This is a rate, right? Oops. This is a rate that's given to us. And that's the rate that what's changing?
Volume.
Volume. The volume of the water, right? The volume of the water. So we should call it dV.
D?
dV dt is given to be 2
Yeah.
pi cubic inches a second. The rate of change of volume, right, with respect to time is 2 pi cubic inches a second. Any questions on why that's the derivative of the volume or the rate of change of volume? I mean, that's what you're pouring in, right? So that's how fast the volume is changing. What do we want?
When it's 1 inch from the top?
What? Yes, but what is it?
We want
What
dH
derivative?
dt.
Yeah. How fast is the water level rising? Well, the water level, we've labeled it as H, haven't we? So
I see now.
dH dt is what we want. At what moment in time?
H equals 3.
At H equals 3. What now?
Find the equation.
Find an equation that relates what 2 variables, Emmanuel?
I believe it's dVt and dH dt.
Yeah, so it's that variable and that variable. It's the V and the H we want to connect together.
Volume of a cone.
Well, volume, okay, volume of a cone, but the volume of the water, right? We're trying, the thing that's changing here is the blue part, the water, right? Not the cone. The cone is fixed. The cone has a fixed volume. The water's volume is changing as it rises.
Yeah.
But yes, the formula we need is something that gives you the volume of a cone. Does everyone agree with that? I mean, we should be looking for an equation that has, we should be looking at something with a cone. I'm gonna put equation right here. So this is where I go to my formula sheets.
I've got
Maybe I
it.
don't. Where are my formula sheets? There we go. So right here on the first page, here's a cone and here's the volume. 1/3 pi r squared h. So here's what I know. I know that when it comes to a cone, right? When it comes to a cone, the volume will be 1/3 pi times the radius squared times h. Any questions? If I differentiate this right now with respect to time, if I do, I'm going to get dvdt, right? Is going to come out of this somewhere. Is that okay?
Yeah.
You have dvt in the
Mhm.
top. Okay. What other thing am I going to get out though?
DHDT.
DHDT. That's good because that's what I'm looking for. But what else?
You need to
DR.
find
DRDT.
DRDT, and that's not good because I don't know anything about R, right? I don't know anything about R. Okay, I'm going to put you into breakout rooms for about, I don't know, 7 to 8 minutes. And I'm going to see if in groups you might be able to figure out how we can still do this problem. And the hint that I'm going to give you, okay, the task of you in this breakout room is to see if there's any way that you can get this relationship to not have R in it, to just have V and H. Kind of like on the previous problem, we had, when Carla had originally suggested cosine, it worked like in terms of it was correct, but it had the H in there and we didn't have anything about DHDT. So we just used a different formula, right? What I'm saying here is we have a formula that has V and H in it, which is great, but it has R. I'm trying to see if maybe in a breakout room, y'all can figure out a way to come up with a relationship between V and H that doesn't have R. Understand? Here we go. Breakout room time. Now, if you know how to do this already, like you've seen it, try and help others stumble upon it. Don't just say it right off the bat. Where's my breakout rooms? I'll put like 4 people in each room, 4 to 5. Okay, so here it is. Make sure you have the problem so you know what you're doing. It's 142. We'll come back at 150. Enjoy. Okay, I think everybody's back now. Well, how'd it go?
We were getting somewhere, kinda. I believe in our team.
Okay, so the idea here is to try and eliminate R from this equation to get it out of here. But you can't just like throw it out, right? You have to do something to replace the R with something else. And that something else needs to have H or V in it. That way the whole
I
equation.
know how to do it, I just can't really explain it. You can compare the two cones using similar triangles, and eventually you can find the relationship between H and R.
I think that you said
Not
that
the-
better than I would have said it, which is you can look at these, you have to look at the general picture. And there's something about this cone, this big cone, and the small cone of water that there's always this proportion that's maintained the whole time. Now, the easiest way to see this is to imagine coming through and cutting the cone in half. Okay, so what if you cut the cone in half, open it up and looked at it from like a cross-section point of view? It would look like a triangle with another triangle which represented your water. I know that the water would pour out if you cut it open. I'm just saying, like, if you could cut it out and open it and look at it, here's what it would look like, right? Now, if we look at this, and let's get in here and zoom in on this. If we look at this, we have right up the center, okay, we have two triangles that we just created. We have a big triangle and then a small triangle. So let's look at those triangles by themselves. Right, if I look at the big triangle, it has this right angle and it has some angle here, right? Now the smaller triangle, which is like red, and then it's got that little blue piece, right? There's your smaller triangle. Also has a right angle here, and this angle is also the same as this angle. They both share that same angle, don't they? So if these two angles are the same, and they both have 90 degrees here, then this angle and this angle have to be the same. So these are what we call similar triangles. And when two triangles are similar, they have a very important property to them. And this is something, I guess, again, you would have to know, okay, coming into this class. So before I get to the property that they have, let me see if we can label some things. Do we know this side of this triangle? This right here. This is the cone, right?
6 inches.
Yeah.
That's
I think it's
4.
4,
Right,
my bad.
isn't it
The
4
4
inches?
inches.
Okay. And then do we know how wide this part is?
6.
3 inches.
The whole thing is 6, right? So we went and cut it in half. So this is 3, right? Now, in terms of our picture here, the H is this side, right? That's H. And what's this little piece? Wouldn't that just be the radius of this cone? The water cone, the cone made out of the water, has a radius of R, doesn't it? Whatever it is, R. Let's call it R then. You following me? Now, the property of similar triangles. The property says this. Given two similar triangles, the ratio of corresponding sides are equal. All that means is this. If I take 3 and divide it by 4, I will get the same thing, same ratio of taking the R and dividing it by H. If I take 3 and divide by 4, it's the same as taking the R and dividing by H. see, these are corresponding sides. These are both the short sides of the triangle. So if you take the short sides and divide it by the longer of the two, you should have an equal proportion. And what's great about this formula is that now what I can do is I can solve it for R. So let's get R by itself by multiplying both sides by H. So I just multiplied H here and H here. H is canceled and I get R is 3/4 of H. Now let's see why that's a good thing. If we come back up to this volume formula, we can now replace this R with 3/4 of H. Now this, we can only do this for this particular cone of water that's within this cup. If we had a different shaped cup, right, then this would be a different, they would be, we'd have a different set of similar triangles, so we would have a different proportion. But for this particular problem, I can replace the R with 3/4 H. And so this now becomes 1/3 pi 3/4 H, that's what R is, squared times H. So I'm going to say this stuff down here, this was just our scratch work here. Right. So you were in your groups. Did any group come up with that idea on their own? I mean, I know, who was it that suggested that? Braxton? Was it Braxton?
Yeah, I was, man.
One of the girls in my group, she was like onto it, but then we had to break apart.
Okay, yeah, I could have left y'all in there for 30 minutes and that probably would have been more useful, but don't have all day, so. Okay, so if you didn't, if you're sitting there saying to yourself, like, I would have never come up with that on my own. Well, that's why we're here. It's for me to show you something and you go, oh, wow, I wouldn't have thought of that. But now moving ahead, I know that I can somehow use geometry and similar triangles to create relationships and then replace variables. And this is just a kind of standard process now.
Hey, Professor, just want to make sure, from that formula, is there any way we can just get out R? So, like, I mean, I just wrote down that formula and got out this R squared equals V over 1/3 pi H.
Oh, you mean solve it? Okay, so could you have just taken this formula and solved it for R?
Yeah.
Yes, but then you still have an equation with R in it, right?
Right.
So if you tried and, I mean, you have to eliminate the R. So you would have R equals something, which doesn't eliminate the R. If you take that and plug it back in here to this one, you would basically get, at the end, you'd get like 0 = 0. Like it wouldn't be an equation you can work with.
Got it, thank you.
Okay, so let's rewrite this equation. It's 1/3 pi. I'm going to go ahead and square the radius, which was 3/4 H. So I square the top, I square the bottom, I square the H, and then I still had an H there. Right, so I have to square top and bottom and the H. And now let's move this out to the front, the fraction. And when I do this, the 9 and this goes in, 3 goes in there once and 3 times. So we should get 3/16 pi H cubed equals volume. And there we go. We have an equation that relates the volume of that water to its height and only its height, right? So now if we differentiate, we're going to get a dV dt and we're going to get a dH dt, but that's all we'll get. And that's okay because those are the things we're given and what we want respectively. So derivative time, derivative with respect to t on the left, derivative with respect to t on the right. Okay, so derivative of the left side is just dV dt. And then derivative of the right side, you don't need product rule because 3/16 pi is a constant, so it comes for the ride. But you do have to take derivative of h cubed, which is 3h squared times dh dt. Chain rule, right? 3 comes out, blah, 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 and then derivative of h with respect to t is dh dt. And I think that's it. I mean, we have everything we want, right? dv dt, we know this. This is 2 pi. H, we know h at the moment in time is 3. And dh dt is what we're solving for. So this is all going to work. So here we go. Here's our solution. We replace things. 2 pi equals 3/16 pi times 3 times h was 3, but then square times dh dt. This is 2 pi equals, let's see, 3 squared, 9 times 3, 27 times 3 again is 81 over 16 pi dh dt. Let's divide both sides by pi. That gets rid of the pi. And then let's multiply by 16/81. And that'll kill off the fraction on the right. We get dh dt. And on this side, 32/81, which I'll get as a decimal. I'm getting about 0.395. I'll just go there. Is dh dt. 0.395 what? Look at your units, h over t. H is the height, t is time. Look at your units up here.
Cubic inches per second.
Inches per second. So the final answer here is 0.395, 0.395 inches per second.
Is it not cubic inches?
No, because h is a measurement of the height, right? And height would be measured in inches.
Okay.
It would only be cubic inches if we were looking for the rate of change in volume. But that we actually were given. The rate of change of volume was 2 pi cubic inches per second.
Gotcha. Yeah.
Got it?
Yes, sir.
Okay, so if you're filling a cup that looks like this, 4 inches tall, 6 inches wide at the top, and you're pouring water in at 2 pi cubic inches per second, then at exactly the moment where it's 1 inch from the top, the level of the water would be rising at that instant at a rate of 0.395 inches a second. Okay.
May I see this problem real quick, please, sir?
You want zoom out?
Just, yeah, right there.
Okay.
There.
All right. All right. So I think I'm going to do another example. But before I do another example, I really just want everyone to take a moment to appreciate the power of what we have now equipped ourselves with in terms of implicit differentiation in calculus. So I'm going to take a formula that you may have seen before, maybe you have not seen this. I'm just going to take an equation from chemistry. If you've seen it, great. If not, don't worry about it. Has anyone ever seen that before?
Yep.
Yes.
What is that called?
Gas law.
The ideal gas law?
Yeah.
This is an equation that has to do with if you have a gas in a container. Okay, so maybe you have a container that has oxygen in it, or maybe it's got hydrogen or helium or something. It's got some gas in here and it's contained, all right? This equation must be maintained within the container. It is the pressure times the volume must be equal to, does anyone know what N is?
It's a constant, I think.
One of these is a constant.
Does Avogadro's number?
Yeah, this one's a constant right here.
Yeah.
This one is the number of moles,
Okay.
which would also, that would be dependent upon what gas is in here. And then T, capital T is
temperature.
Temperature. Okay, so these two are the only constants in the problem. Pressure, volume, and temperature are variable. What I mean by that is if you increase the pressure, right? If I increase the pressure, then the left side of the equation gets bigger, right? And in order to maintain equality, that means the right-hand side has to get bigger, which means your temperature has to go up too. So if you pressurize the gas, then the gas gets hotter, all right? Or it gets warmer in there, temperature goes up. On the other hand, if you decrease the temperature, the pressure, then the temperature will also go down to maintain the equality, all right? This law is very important. I'm about to go off topic a little bit here. Many of you use air conditioners, right? We all use air conditioners, right? So we appreciate air conditioners in Texas, don't we? Definitely appreciate, okay? So air conditioners work on this principle right here, okay? So the way it works, the way an air conditioner works is you have a pump. This is going to be a very, very generic illustration of the way an air conditioner works. You have a pump, and in this pump, you pump Freon. Okay, Freon is it's a liquid, but it's also a gas. Okay, it depends on the temperature. Okay, so when it's hot, it's a liquid, and when it's cold, it's a gas. So what happens is you pressurize it, okay, and you pump it down this tube. And then at the end of this tube, there's a little hole, okay? And then the tube continues. So there's a little orifice in the tube. And so on this side right here, you have very high pressure. Because all this gas is trying to go through this tiny little hole. Once it comes out the other side, it's very low pressure. So what happens is that you go from high pressure to low pressure, and anytime you lower pressure, you lower temperature. So when it comes out, when the gas comes out the other side, it's super, super cold. Not just cold, super cold, okay? So you have a super cold gas now that's in this pipe, and you run that pipe back and forth like this. And then you bring it back over here and you pump it back through. Okay, so what happens is gets pressurized, gets spit out this little orifice, comes out extremely cold, and then runs through a pipe, starts to warm up, gets warmer, 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 and then goes back through here and gets repumped and recirculated and just continues this cycle over and over and over. What you do is you put a fan here. That's a fan, looks like a flower.
Flower.
It's a fan, okay? And you blow air over those coils. And remember, those coils are super cold because that gas came out super cold, right? And so the air coming off the other side of those coils is cold. And that's what blows out your vents in your house or your air conditioner in your car. You're getting, it's not cold air that's being made, it's cold wires or cold pipes that are being made, and then the warm air is traveling over the cold pipes. Okay, So when it comes back through here, now, if it's your air conditioner at your house, this actually goes outside your home to that thing that's sitting outside, that big fan. You know, outside your house, you have that thing.
Yeah.
Okay, so out there, what's happening is this pipe is coiled around, and then you have another fan over here that's blowing. And what it's doing is it's taking the pipes that now have hot gas in them because they've come through here, they've been warmed up, and it's basically blowing air over the hot pipes, and that's actually removing the heat from your home. So when you go outside to your air conditioner in the middle of summer and you put your hand over that thing outside, you put your hand over this, it better be hot air coming out, like really hot air, because that's the heat coming out of your house. Right? That's the heat coming out of your house. Think about it this way. I'm really going way off here. This air that's being blown in over here is hot. That's the air in your house, right? When it goes over these cold coils, here's these really cold coils. How does heat travel? Does heat travel from hot to cold or from cold to hot? Do y'all know? Never mind. It doesn't matter.
Hot, cold, isn't it?
The heat here is transferred onto the pipe, and then that gas in there becomes warmer, right? So then when it comes over here and goes outside and gets blown out, that's the literal heat out of your home being removed. The cold gas coming through here has absorbed the heat from your house and has taken it, and then you blow it out, and then you recirculate it and just do it again and again and again and again, over and over, and you eventually cool your house down. Everything, though, is dictated by this equation. All right. Now, why am I bringing this up? Because now that we're calculus students, if I want to know how fast the temperature is increasing or decreasing at a specific moment in time, then all I have to do is differentiate this equation with respect to time. So I'm going to do that. I'm going to take the derivative right now with respect to time on both sides. So if I take the derivative on the left side, both P and V are both variables, so I must use the product rule. So I do the derivative of P with respect to time times volume plus the derivative of volume with respect to time times P. That's my product rule on the left side. Equals, now on the right side, N and R are constant, so I just leave them there. And then I just take the derivative with respect to capital T, or sorry, with respect to little t of capital T. So this will be d capital T over d little t. And this right here can be used by anybody to now determine instantaneous rates of change of anything you want. If you want to know the rate at which the temperature is changing at an instant in time, then you're going to need to know this, and those other things are constants. So you would have to know all four of these things in order to answer this. You'd have to know how quickly the pressure is changing. You need to know the volume. You need to know how fast the volume's changing, and you need to know the pressure. If you knew those things, then you could calculate how fast the temperature is changing at that instant in time. And this goes for anything. I mean, I could solve for any of these. To solve for that one, I would have to know this, and that, right? But the big picture is this works for any equation, any equation. Doesn't have to be the ideal gas law. It can be E equals mc squared. It can be any equation, it can be differentiated with respect to time. Does that make sense? Like, this is a super, super powerful thing that we have now.
Quick question, is NR the number of moles or is it just N?
I believe that N is the number of moles and R is Avogadro's number. Now, I'm not a chemistry major. I haven't seen this formula since I took chemistry many, many years ago, but I'm pretty sure it's number of moles and Avogadro's number. You can correct me if I'm wrong later, but I don't really care if I'm wrong. I'm pretty sure these are constants. Okay. So we should do another problem. We have a little time still.
Woo!
All right. So I'm just trying to figure out which one I want to do. There's so many problems that you can do when it comes to related rates. I can show you 50 problems, and then the next problem I give you would be completely different. So it's all about setting things up and understanding the geometry.
Can we do
So-
the one with the runner?
Oh, the runner.
Or is
Yeah,
that not
I
really going
I
to be
could do
relevant?
that one. I could do that one. I'm just kind of bored of that one, but yeah, we can do
Okay,
it.
no, we don't have to do that one. If you find something, I mean, if there's something more exciting, I'm down. I'm just looking at
No,
the
no,
stuff that
that's
we
a
have.
great problem because of that's a great problem because of the equation that you need. That's a really tough problem. Let's do something a little easier, and I wouldn't give you a problem like the runner on the test anyway, so let's do something more like what I would give you on a test, okay? So how about this? Sarah, oops. I'm just gonna make this problem up. Sarah is 30 feet due west of, of Tom, okay?
Somebody has asked, are the universal gas constant, which has value of 8.3144 joule mole multiplied kilo.
Somebody's asking me about what?
I wasn't asking, I was just
Oh, you were
saying
stating it. You were stating it. Okay, so what is it? Let me see.
just a fun fact.
Oh, universal gas constant? Yeah. So that's what the R is in the formula. Okay, thank you, Liz.
You're welcome.
So it wasn't Avogadro's number. Where did I getting Avogadro's number from then?
I mean, Avogadro's number is used a lot, so.
Yeah, okay, that could just be my holes in my memory. All right, so Sarah is 30 feet due west of Tom. She begins running north at a constant rate of, how fast is she going to run? Let's say 20, no, that's too much.
No, make it okay.
Feet per second. Two minutes later, Tom begins to run due east at I was going to make him go faster, but I don't want him to get pissed off, so I'm going to make him go slower. 5 feet per second. .5 minutes. I can't type. I have a new keyboard and it's really hard. It's like really small. I'm trying to get used to it. 5 minutes later, how fast is the distance between them changing?
I see West and I think of SpongeBob when he says West. He said to go east. Oh, I thought you said West.
I
like
have
myself on that.
never watched SpongeBob ever in my life. I think I was at a party one time and it was on the TV, and that's probably the only time I paid attention to it for more than like 3 minutes. I'm serious.
Best party of your life.
So am I missing out? Do I need to watch SpongeBob or something? Or can I move
I
on?
just said we can move on, but I'll send you a clip.
Okay. All right, so Sarah and Tom are I guess they just broke up. They're running in opposite directions, it seems. Sarah's 30 feet due west of Tom. So let's just start drawing a picture, okay? Because I think to get our heads around what's going on here, we need pictures. So let's draw Sarah. Here's Sarah. She's that dot, Sarah. And here's Tom. Here's Tom. He's that dot. And she is 30 feet due west of Tom. Okay, so there she is. That's the beginning scenario, right? That's the beginning situation right there. Agreed? Now, she begins, change this. Sarah begins running north at a constant rate of 8 feet per second. Okay, so she's going to start moving north. So she's going to start moving that way. I'm just going to put it here, 8 feet per second. That's a speed, isn't it? So the arrow just represents that she's going to start heading in that direction. 2 minutes later, Tom will begin running due east at 5 feet per second. So Tom is going to start going this way, and he's going to be going at 5 feet per second. 5 minutes later, how fast is the distance between them changing? All right, so I think the only way for me to get my head around what's going on here is I'm gonna have to draw this like at different snapshots in time. So like, here's the beginning situation. Sarah, Tom, 30 feet, right? Okay, what's the next moment in time we know about? This, let's call this little t equals 0. That's the beginning moment in time. That's where they are. She's like, I'm done with you. He's like, good, I'm done with you. And she's, I'm out of here. And she takes off, right? So she starts taking off. 2 minutes later, so she starts moving, right? So 2 minutes later, I put t equals what?
2 minutes.
120 seconds.
120 seconds. So we have to pay attention to the units in the problem, right? So if everything is in feet and seconds, right, then we need to make sure our time is in seconds too. So 120 seconds later, what's happening now? So I'm going to draw in gray where they started. So here was Sarah in the beginning. Tom is still there, right? Tom's still there. He's like, wait, hold on. I didn't mean it, right? So he's still there, and she's like, she took off, right? She's been moving for 120 seconds now, right? She's been moving for 120 seconds. And how fast is she going?
8 feet per
8
second.
feet every second. So let's just do some math. 8 times 120. So where is she at? That's where she is, right? What's that distance here?
Like 9.
I think it's 920.
920 feet. Everyone understand that's just 120 seconds at traveling at 8 feet per second. Now we are assuming that she's traveled 8 feet per second the whole time, okay? Like, it's impossible to start from 0 and instantaneously get to 8 feet per second, but to make the problem easy, that's what we're gonna do.
No, it's
Okay.
960.
Isn't it 960?
Is it 960 or 920?
It's 960.
It's 3.
It's 960, I guess.
960, okay, all right. 8 times.
My bad.
800, yeah, 960. Okay, we good? So
Yeah,
she's out of here. And then after 2 minutes, Tom's like finally realized, you know what? There was that other girl that had called me last week. So he's like, I'm gonna go, I'm taking off. I'm out of here too. Fine. So he takes off. Swear to God, I'm gonna lose my job one of these days. All right, so now he takes off when? Well, 2 minutes later, Tom begins running, right? So it's at this moment right here that he starts running, right? At this moment, he starts running to the right. So what's our next moment in time that we're interested in or that we know about?
5 minutes after that.
300.
5 minutes after that.
300
Right?
seconds.
5 minutes after that. So that would be our next moment in time. T would be, what's 5
300.
minutes?
420 seconds.
Yeah, 5 minutes at 60, that'd be 300, right?
Yeah.
Seconds later, but then 120 seconds is already passed,
Laps. Okay.
right? So what did we say it was just now? Sorry,
420.
420.
420. seconds. Please understand that this is 5 minutes. It's 5 minutes from here to here. From here to here was 2 minutes. Can you already see that this problem is way different than any problem we've done? Like it's not just like general instant given one equation differentiate. Like I'm having to actually like draw pictures to help myself understand what's going on. Right?
Right.
So here's where we are now. We have where Sarah started, where Tom started. Now, where's Sarah? How long has she been traveling for now at this moment in time?
7 minutes.
Yeah, where's my cursor? Get over here. There we go. She's been traveling for 420 seconds in this picture, right? At 8 miles per hour, or 8 feet per second. So she's now here. So she has now gone 3,360 feet, right? And Tom, on the other hand, where's he?
He's been traveling for 5 minutes.
He's been traveling for 5 minutes, which is only 300 seconds, right? 300 seconds at how fast?
5 feet per second.
5 feet. So he's traveled how far?
1,500 feet.
1,500 feet. This is actually the instant in time picture. Do y'all see that this is the instant in time? Oh, I should include the t equals 420. Do y'all see that this is the instant in time picture? Do y'all see a triangle? Because we are interested in how fast is the distance between them changing. So we are interested in this right here. Let me do it in red. We are interested in this right here, that distance. We want to know if they were tied together with a rope, how fast would that rope be coming out of one of their hands, right? Now, is this a triangle you could solve? Do we have all the sides that we would need?
Yes, we
Yeah,
have
we do,
that
because
gap.
yeah, the gap is 30 though, right? It's not drawn to scale, but this is 30 feet. We do know that, right? Because that's what they started, 30 feet apart.
Mhm.
So we could solve that side. All right.
Can we solve this as a 2 triangle, or we just follow as a 1 triangle? Like
We just do one triangle, and we would say that this side is 1530, and then this side is still 3360, right? And we could now solve this using Pythagorean, couldn't we? But that would just give us how far apart they are. That's not the question. The question is how fast is the distance between them changing? So this is my instant picture. I'm still missing my general picture, right? My general picture is missing. And you can make the general picture very complicated, or you can keep it simple. And I like the simple idea. Sarah, Tom. It's over, Tom. She takes off, right? Let's call this Y because it's vertical, okay? And then Tom takes off, right? And he starts moving this way. He takes off later, right? But he does take off eventually, yes? And let's call this distance here X. So what I mean is Y is the distance from here to here. And X, let's let that be the distance from here to here. Those are variables throughout the problem, right? This is my general picture. Sarah's traveling north, so Y is changing. Tom's traveling east, so X is changing, right? If I draw it like that, then what's given to me?
We have initial distance.
What's given? Sarah, right, begins to run north at a constant rate of 8 feet per second.
So we have dy over dt.
dy dt, that's Sarah, right, is 8 feet
We
per
also
second.
We also have dx dt.
dx dt is Tom's speed is 5 feet per second. What do we want?
The d of the hypotenuse over dt.
Yeah, so let's draw it in this picture. Here to here would be our hypotenuse. We need it labeled here. This would be our hypotenuse. We want dh dt. And when do we want it?
At t
what?
equals 420.
At what?
T equals 420.
We could say t equals 420. I agree. We could say that. In fact, I'll write it down. T equals 420. But see, t doesn't really help me because in my picture, I need to somehow be able to plug this into my picture. So here's, Austin, here's t is 420. At t is 420, can you tell me what y or x would be? Just look off the instant in time,
Yes.
right? Wouldn't this is y, isn't it?
Yeah.
So another way of saying t is 420 is just saying y is 3360, right? I need to go back to my general picture. I just want to point out to everyone again, remember, this is 30. All right, you ready? I think we have everything we need. We need an equation. Now watch this. We need an equation that relates y, x, and h together. The two given variables to the one we want. And we have to look at the general picture. Do y'all see what it is?
Pythagorean theorem.
Pythagorean, right? Now be careful, because what's this side? It's not x, it's what?
X plus 30.
X plus 30 squared plus y squared must equal h squared. So I'm going to write that down. The equation we want is x plus 30 squared plus y squared must equal h squared. Differentiate with respect to time. Take 2 minutes to differentiate this with respect to time on your own. 2 minutes. I'm going to write the derivative down while y'all are still doing it. Careful with that chain rule on the x plus 30. Okay, I think that that's enough time. Hopefully you got this. And we're trying to solve for dHdt, which is right there. But now we can look at this picture. We can look at this now. So we know at the instant in time, we know what x is, right? Isn't x 1500? dx dt is 5. dy dt is 8. Running out of colors. Y is that. H, oh crap, we never got H, did we? H would be that hypotenuse. And the way we get that is to do 1530 squared plus 3360 squared equals H squared. Just using this entire side plus squared plus that side squared. Let me do that real quick. Has anyone done it yet? No. I get that this side is 3691.95.
Yeah, that's what I do.
Okay, I'm plugging everything in now. Here we go. 2 times 1500 plus 30 times dx dt, which was Tom, plus 2 times 3691.95 times dy dt, which was Sarah, equals 2 times, oh wait, hold on. I put the wrong thing for y. I apologize. I put h in there for y instead. 2 times, here's where it is. I'm gonna run out of room now. Sarah, 8 equals 2 times h. Here's the 3691.95 and then times dh dt. Okay, I'm just going to get the answer and just give you the final answer because I'm running out of time. If all my math is right, all my arithmetic, I'm getting 9.35 is approximately dH dt. And that's going to be 9.95 feet per second. Feet because h is a measurement of distance. Distance in this problem is feet and time is in seconds. Oy, oy, oy. Okay, so at this point, their relationship is growing apart at a rate of 9.35 feet per second. So I hope that illustrates just, you know, how different a problem can be, but that we can still do it as long as we get things set up properly. Questions?
Did they ever get back together?
A good question. Stay tuned. The next chapter, chapter 3, we'll find out what happened to Sarah and Tom. I just tell you, don't get your hopes up. All right. He had issues. He had lots of issues.
Got it. Yeah,
Oh.
I guess so. You can be a screenwriter at least, you know.
Yeah. That's pretty entertaining stuff, right? All right, so here's your review, right? So I hope that this has gone okay for you. Like I said, your test will not be like exactly this. I just feel like if you can do this, you're going to be in good shape. Just be prepared for, like, I think I only gave you one problem on the test like this. Find the equation of the tangent line. But just be aware that on any one of these, I could have asked you that. I could have said, hey, you know, look at this function, find the equation of the tangent line. Which means you still have to do the derivative, but then you have to figure out like what the slope is at a specific point. So just be prepared for that sort of thing. Yeah. I don't think I have anything else, but you know, make sure you come on Thursday with your camera set up and so that we're not wasting a bunch of time. trying to get people to get their cameras right. And make sure you sleep and eat.
Are we going to need a calculator for this test?
I would have a calculator for sure. Yeah.
How many questions is gonna be on the test again?
I don't know. I haven't written the test. So I think that this review is probably, I mean, look at these word problems can take 20 minutes, you know, depending on how it goes for you. It'll be similar in length. I think that this review is similar to the length. I think 8, 9, and 10, or sorry, 8 through 11, I think those can start to take up some time, but I'll try and make it where you can finish it in an hour, 20 minutes, because we'll spend 20 minutes just getting everything set up. So, yeah. All right, everyone. Is that it? You can go.
Oh, well, just wanted to tell you guys the registration start on the 5th for fall.
Oh, the registration for the fall?
Oh,
And also, if you're a full-time student, you can take up to 9 credit hours for free in summer.
oh, good.
And
Oh, yeah,
I'm
yeah.
broke.
Right. They're doing like free tuition. And then in the fall, I don't know if any of you are going to be around for the fall, but for the fall, I am teaching face-to-face on campus.
Oh,
Half of my schedule is on campus, the other half is not. And it'll be true like face-to-face twice a week. There'll only be like 12 students in the class because we have to social distance.
mhm.
But I think I'm doing Cal too. So you know,
Oh,
just as a heads up.
That's the
I
hard
have to
one,
double
right?
check it.
so
but
if we,
The what?
oh, so if we don't get into your face-to-face class, you're still gonna do it like this on Zoom? Or is it gonna be like the pre-recorded solely online kind of business only?
You know what? Honestly, I don't recall at the moment. If you want to wait for a minute, I can tell you exactly what I'm doing.
Yeah, because I'm gonna see you next semester.
Let's see if it's in here. Fall 2021. Hold on. Should have a note here somewhere. Yeah, okay, so I'm doing a college algebra on campus, which doesn't matter to you all. That's a 1414 college algebra. Yeah, it's oh shit. It's a 9 a.m.
Oh my God.
Yeah.
That's not bad.
I have to leave my house 1 hour